All right, so I've been working today on calibrating the zero crossing for the current sensor. So when you have a linear function, you have two errors you can have. You can have a gain error or you can have an offset error. And you can specify pretty much any piece of test equipment that behaves linearly with a gain and an offset. It's y equals mx plus b. We care about b, the offset, where we cross our zero. So here's a sensor that I took empirical data on, and what we are trying to do is adjust the zero crossing here. In this case, it's the y zero crossing because of the way this graph is shown. But one thing I wanted to point out is that the OEM current sensor, which is sitting right here and we're running a test current through it, the data we gathered with the onboard unipolar circuit that I designed has an R-squared value of 0.999995, which is pretty incredible. If that value were 1, it would mean that the actual data we're gathering from that sensor is perfectly linear. Because it's 0.9999995, that means it's essentially perfectly linear. It's certainly more linear than our 10-bit ADC can even digitize. So pretty neat to see it. That's mostly just the fact that the current sensor that Honda bought from Denso, I think, makes it. Yeah, it's Denso. It's a very well-designed current sensor, but we've been able to keep its linearity through our analog circuit. The main way we've been able to keep that is that the measurements we're taking are ratiometric. So the voltage reference itself is partially powering the current sensor. The return voltage on the current sensor is 5 volts. That's also the reference, is the same 5-volt source. So anyway, very, very linear. Now what we need to do is we need to be able to control the offset. So between PCBs, just because of the tolerance of the parts, the tolerance of the ADC here, all that stuff, you get errors. And so the zero crossing is nominally 332 counts from a 10-bit ADC. So if the ADC returns 332, that means it's 0 amps. But in my testing on the 18 boards, I was seeing values between 330, maybe as low as 329, all the way up to 337. So that range there represents every 5 counts is approximately 1 amp. So that's about a 2 amp difference. So if you have a 5 amp hour battery in your car and you have a 2 amp zero crossing error, then that's going to mean that after driving your car for 2.5 hours, you're going to have a negative recal. Obviously, we don't want that. So what I've come up with is an algorithm that actually finds the zero crossing. And the way it does that, this eluded me for a minute. Like, how do I know when there's no current through the current sensor? Well, there's no current through the current sensor when the car is off. Duh, right? It's in hindsight, it's really obvious. But so, and LiBCM stays on all the time. So what LiBCM does now, and I've just gotten this working, is when you turn the car off and the key turns off, we basically run an algorithm that essentially gathers, whatever the value is and says, okay, we know because the IMA system is off, we know this is 0 amps. Now we do some formatting on it. We take, I think it's whatever the num samples per ADC measurement is. Right now it's set to 64. On the Rev C hardware it goes to 8. We're going to take 8 measurements. We're going to make sure all those measurements are the same. Because if the measurement values are changing, then that's a sign that maybe the current sensor is not off. So every count is about 200 milliamps. And so we need, I think it's 8 on Rev C, it's 8 counts in a row that are exactly the same. And once we get those, we make sure that they're within close enough to that nominal 332 count value. So obviously if the current sensor were to calibrate the value of 600, that would mean you have at 600 maybe, I don't know, like 5 by 5, 60 amps going through the battery. Is that right? I don't know, whatever. Let's just say 60 amps. You obviously don't want to have a 60 amp offset. That means that there was in fact current flowing through. So anyway, this algorithm seems to work pretty well actually. It's just running unbounded right now, so you're just seeing this all flashing by. But you can see that right now the result is 332 because there's no current flowing through the sensor. If I turn the sensor off, it's the same thing or whatever. This power supply is just pushing current through that current sensor, and it's just a 1-to-1. This other loop I'm not using right now. So if we come through here now and we raise the current to This is 100 milliamps. You can see we just popped up to 333, and you can see now that it's eventually going to get, I guess we're going to have to go up to like, there's 334. So this would be, obviously you don't want current running through there. Again, we're trying to calibrate the tolerance stack up basically on all of the offset errors on the Arduino, the power supply, I'm sorry, the current sensor, etc. So in this case, the value we'd be setting would be 334. Now in the code I'm running now, we're not actually setting the value. This is just spitting it out so that I can see it in real time and I didn't have any kind of delay or whatever. But you can see as we add more and more current, which would be more and more, ADC reference issue, we're now at 335, we're now at 336. Eventually though, it's going to be too far out of bounds, and I believe that limit is at 338. Yeah, so, and now it's just telling us that here. What I can do is just stop this by unplugging it, and we can actually read. Maybe unplugging it, there we go. Sorry. Current sensor offset exceeds limit using last valid offset. So this code will normally run one time each time the key turns off. And so it's telling us here, hey look, we did measure all of our values, the 8 values or the 64 values. They were all 338 in this case, but that exceeds the limit, which is 338. So anyway, that is current sensor offset. And so what is this going to do in your car? It's going to mean that every time you turn the car off, we're gonna figure out the state of charge when the car is turned off. What we'll do is when the key is first turned on, no matter what, when the key is first turned off, we're gonna start a timer. And after 10 minutes, the battery will have settled. So if you were doing severe assist and there was some voltage depression or whatever, or you were regenning and there was some voltage elevation or whatever, after 10 minutes, my data shows that's gone. The battery has settled, the chemical reaction is at least stabilized enough that the voltage does not change. That's the data I posted yesterday about, maybe 2 days ago now, about the battery. I was charging it at 50 amps and it was 4.17 volts, and then after 10 minutes it was 4.09 volts, and then after 12 hours or whatever it was still 4.09 volts. So what we do is we wait 10 minutes after the key turns off, we look at the cell voltage. And using that cell voltage, we determine a new state of charge. So every time you turn the key off, we eventually, after 10 minutes, will determine a new state of charge. Then when you turn the key on, we will use that state of charge, but now because we're pulling current in and out and the battery voltages are no longer stable, because again, we're pushing and pulling current, as long as the key remains on, we need to use this current accumulator, which basically every 100 milliseconds or whatever we set it to, we'll look at the current over the last 100 milliseconds, and it will, if the current's positive, it will add to a number, and if it's negative, it will subtract from that number. So this is a 32-bit signed integer, and it's counting current, so it's just counting coulombs. And we're using that to figure out where the state of charge is. So for example, if the battery is 3.75 volts, and if that's 60% state of charge, I have no idea, then as soon as we turn the key on, we say, okay, the state of charge is 60%, and oh, we're pulling 1 amp now? Okay, so every second or whatever, we have 1 coulomb added to that accumulator. The accumulator is not in coulombs, it's probably gonna be in like microcoulombs or whatever, wherever it is that I don't overflow a 32-bit counter after like 15 hours or whatever. I assume no one leaves the car on for more than like 15 hours. Maybe it should be 30 hours, who knows. Probably won't matter at the end of the day. But the thing is, while the car's on, we don't want it to negative recal. And so what this code here does, even though it only changes the value by up to 8 counts in any direction, keeps you from having that negative or positive recal. Now, one caveat here, it's not like positive and negative recals are not going to go away, particularly when you drive your car for a long, long time. If you're driving 12 to 15 hours, you probably expect that there's going to be 1 negative recal or whatever. And the reason is that the resolution on our ADC is only 10 bits. So it's only 200 milliamps of resolution. So we can't detect current less than that. Now in the long run, if you're assisting and regenning, it probably kind of averages out. But at the end of the day, our resolution is only 200 milliamps. So if you have a 5 amp hour battery and you have 200 milliamps of resolution, If you do the math there, it's 25 times. You would expect that you'd have a negative recal at least once every 25 hours of driving with the car continuing to stay on. Again, every time you turn the car off, we're going to just determine the state of charge again by looking at the battery voltage. So that's kind of the algorithm I'm working out right now for the state of charge. So basically, when the car is on, we'll only be looking at the cell voltage kind of for hard limits, like 4.2 volts or whatever, 4.1 volt, depending on what the regen current is. If we hit that 4.12 volts or whatever, then we will force regen to stop. On the other end, if we hit the 3.47 volts or whatever it was on the assist side, we will stop there as well. But we shouldn't hit those limits because we'll now be using our current accumulator, which will say, you know, this battery has 2.9 amp hours in it. It is a 5 amp hour battery. So if we then later on get up to 4.5 amp hours, you know, just for example, we will start to slow down the regen at 4.5 amp hours out of 5 or whatever. Obviously we're using less. We're not using the whole range of the capacity. I'm just kind of as an example. On the other end, when you get down to 0 amp hours, you know, maybe at half an amp hour, we will start limiting the assist. And that way we can do it a lot more gracefully than what we do now, which is we're just watching the voltage. We hit the voltage, we immediately enforce a limit. So that is a long explanation, but it's just kind of what is going on to make the current accumulator work correctly. There's a lot of smaller pieces that have to be made. And anyway, as always, thanks for watching.